Let's welcome Nikhil. Thank you. Chicken dinner.
My name is Nikhil, and my passion project is on gravity and why it's not like the other forces. First, we will cover why I chose this topic, then we'll cover what gravity is, then how space-time is related, and finally we'll cover how gravity is unlike the other forces. So let's start with why I chose this topic. I chose this topic because when I was learning about Newton's laws, I found gravity to be a very intriguing concept. There are many articles talking about why gravity was not a force or unlike the other forces. This got me very interested because I wanted to learn more about this. I never heard something like this before, so I researched a lot and I'm happy to share my findings with you. So, question 1. What is gravity? Let's talk a bit about gravitational pulls. When you think of gravity, you might think of two planets being attracted to each other or colliding. But gravity can be with anything. You and a rock could have a small gravitational pull to each other. The reason you don't move because of this is because the Earth's gravitational pull is so large that it anchors you down. And this is not just scale. The pull would be much smaller than this compared to the Earth. Let's talk a bit about Isaac Newton. He had 3 laws of motion, but the one we'll be focusing on is the second law. The second law is that the force you need to apply to move an object is equal to its mass multiplied by its acceleration. This actually has a lot in common with gravity. Now this raises the question, what's the difference between weight and mass? Weight is basically mass times gravity. So if you're on a different planet, you would have a different weight, but you would have the same mass if you're on a different planet. So that's actually very similar to force is equal to mass times acceleration, because the gravity is just the acceleration in this case. So let's say you weighed 75 kilograms, your mass was 75 kilograms. You would weigh 75 times the gravity of Earth. This is around 735 newtons. So on the Earth, you would weigh 735 newtons and have a mass of 75 kilograms. And on Mars, you would weigh 75 kilograms and have a mass of 280 newtons. Now, since there's a formula for weight and mass, shouldn't there be a formula for gravity? There actually is, and it looks kind of confusing, yes. So let me break it down. This is the gravitational constant, which is around 6.6 times 10 to the negative 11. This is the mass of the object number 1. This is the distance between object number 1 and object number 2, and this is object number 2. In a more visual sense, let's say Earth was mass number 1, Mars was mass number 2, this is the distance between them, and this is the gravitational constant. Now, if you're a space nerd like me, you might want to know the actual force between Mars and Earth is. So here it is, it's 1.165 times 10 to the 26 newtons. But Newton's gravitational theory was not 100% accurate. That's where we get into question 2.
I didn't read it.
It's fine, I'll show you later. So question 2 is, how is space-time related? What is space-time? It's basically the fabric of reality. That might sound a bit complicated, and it kind of is. Most people think of it as a canvas on which objects sit, but I don't like to think of it that way because that suggests there's a large gravitational force keeping everything glued to the canvas. It's more like when you're near a massive object, all objects move in a straight line, but the plane in which they're moving is curved. So space-time bends objects' paths, and is also bent by objects. But space-time is not 3D like most people think. So Albert Einstein had a few theories about this. Back in his time, most people were thinking that space was a 3-dimensional thing, and time was a different 1-dimensional thing. This is possible, but Einstein was thinking about how it would be if they were integrated into each other. This would mean, as I said, space-time bends objects' paths in motion, and in turn, objects bend space-time. So if you combine spatial dimension, a 3-dimensional dimension, and the time, you get a 4-dimensional dimension. So in most representations, they show space as a 2-dimensional object, so you can actually represent space. A cool thing is that space-time ripples near massive objects. So near the sun and neutron stars, it dips really low, and also near a black hole. But if there are 2 black holes orbiting each other, it actually ripples around. This is why objects get spaghettified. They get stretched out around black holes. So, as I said, space-time serves everything with mass. And light is made up of photons, which have tiny, tiny masses. So even light curves around objects like the sun. This is actually proved by a guy named Arthur Eddington, who was proving Einstein's theory. This is the actual photo of how he proved it. He took a photo during the solar eclipse and saw where the stars were, and he also took a photo in the night, and the stars were in a different position. The true position of the star was actually much farther from where it appeared during the solar eclipse because of the sun's gravity. Now, we move on to question 3. How are gravity and spacetime related? At this point, we see that Einstein thought gravity was not a force, and Newton thought otherwise. Let's explore the possibilities of Einstein's theory. Spacetime and gravity seem very similar. Actually, they're almost the same. Gravity is nothing but the curvature of spacetime. So, if you were here, if you were near a massive object, you would be moving in a straight line, but the plane you're moving is curved, which is basically gravity. So let's talk a bit about relativity. Let's say you were in a rocket ship that was accelerating upwards at 9.8 meters per second squared. It would feel the same as if you were accelerating onto its floor at 9.8 meters per second squared. So it kind of simulates gravity. Now, this could actually be what's happening instead of gravity. Maybe the ground is actually accelerating up towards us. This might sound crazy, but it's just a theory. If the ground is accelerating up towards us, it would mean that the Earth is expanding. So why don't we see it expanding from space? This could be because there is a way to change your position without changing your spatial coordinates. It's kind of complicated, but I tried to break it down from the website that I found this from. So this is the position and the change in position, and this is the acceleration. This is the term that refers to curvature of spacetime, basically gravity, and this is the velocity through time. So if we make the change in position 0, we can see that the acceleration has to be equal to the curvature of spacetime times the velocity through time. So this is possible, which means that you have to accelerate just to stay still in curved spacetime. This is where it ends, because people are still exploring this and have not found answers to this theory. But yeah, this is where it really ends. Because of COVID, people weren't able to get to the test scenarios. Well, yeah. Thank you for listening to my passion project. This is my bibliography. And any questions?
Any questions? Nikhil, so maybe I missed it.
Yeah.
When you were talking, what kind of research were they doing when that COVID ended up shutting it down?
So they were trying to see, there was a theory about a particle, a charged particle. If it was falling, it would appear positive, and if it was not falling, it would appear negative. So in this case, maybe the Earth was expanding towards us. That means it would appear negative because it's not falling. But they couldn't do that because of COVID.
Was this the large, what's the one over in Europe, the particle collider that they built that became, like, took over for the one at SLAC? What's it? The Hadron, something like that. Is that where they were doing the work, Nikhil?
No, because the Hadron Collider collide like two atoms to make a new element.
So that's not
the place.
Oh.
It's not very famous. Like, this theory is just, they're just trying to see if this could be a possibility.
Awesome. Sounds fascinating. Does anyone else have any other questions for Nikhil? Noya.
So what did can you go back to like this lab where you like showed a picture of Einstein's thing or
Yes. There.
next one?
Next one. This one. This one. This one.
There's like the Einstein saying something.
Are you looking for the meme that he had?
No, the
Okay.
one.
What?
The solar eclipse.
Brynja.
Oh, the solar eclipse picture is back. Yeah.
Yeah, we go back.
Wait. I have 28 slides. Okay, I'm trying to navigate them. Where was it? Yes.
Noya, are you trolling Nikhil right now?
No, so that's like the actual photo from May 29th.
Yeah.
Is there like because you said that like when he came back at night, the star left his position.
Yeah.
So like was that like saying that like because there was the light, it looked like the stars were in the position?
No, it is because the sun curved the position of the light. So yes.
So if you see, if you look at the graph he has, it shows you right there where the star actually is and where the star appears to be
Yeah.
because of the curvature. Another question, Mr. Dowgan.
Yeah.
Michael, what do you think of loopholes? No, wormholes, I'm saying. Like, I'm thinking of space
We
time,
know
I'm always
he
thinking
thinks
of
of
in like
loopholes.
Review, where they like take they have like a note card to show what a wormhole is. Would that match with what you found with like the definitions of time and space time being like one-dimensional versus integrated?
So a wormhole, I think, it's just like it transfers an object to another point. So how that would look in like space-time terms is like there's a hole in space-time and then it connects to like another plane. So I mean, it could be possible.
Do you think it would look like the example I always show is like a paper and then they put punch something through it? Do you think that's accurate or not a great representation of it?
I mean, I think that's a simple representation of it. I mean,
Wouldn't that be kind of the equation that he was just talking about?
Yeah, I think it shows back if you go back to the space-time one.
which space-time one?
Right there.
Here?
That would be it essentially. Is if you could change your place in your position in time, that would essentially be it with the wormhole.
Yeah.
Radical. Okay, thank you to people. Thank you, brother.